So in the previous set of videos, we talked about introduction to digital communications. We talked about signal space concepts. We talked about representation of the signals in the vector domain, where you have finite number of basis functions which span your signal set S. And then we also talked about the maximum likelihood decision criteria and how you can detect what kind of a receiver structure would allow you to have a maximum likelihood decision criteria. And then towards the very end, we started talking about once you have received the signal, how would you compute the error probability? We talked about some of the bounds last time, and we said that, for example, one of the bound, which is not very tight bound, is called the union bound of error probabilities. We said that the probability of error, remember this is the symbol error probability, using the union bound is less than or equals to m minus 1 times q function of d min over root 2 n naught, where we said that the q function is nothing but the integral of the tail of a standard normal Gaussian random variable. That means where q of z is nothing but integral from z to infinity 1 over root 2 pi e to the power minus t square by 2 dt. And we said that this q function is less than or equals to 1 over z root 2 pi e to the power minus z square by 2. This is a bound which is tight at z greater than 0. So if we make use of this bound, our union bound for the error probability changes to m minus 1 over d min root pi over n naught e to the power minus d min squared over 4n naught. So this was the union bound. And then we also talked about what is called the nearest neighbor approximation. And the nearest neighbor approximation says that your error probability, symbol error probability, always here, is the minimum number of nearest neighbors times q function of d min over root 2 n naught. Here we can remark that if your capital M is equals to 2, that means you're talking about a binary transmission, this nearest neighbor approximation is exact. That means if M is equals to 2, your probability of symbol error is nothing but Q of the min over root 2 n naught. This is your symbol error probability. And then we also talked about the conversion of the symbol error probability into the bit error probability if you have used what is called the gray coding, where the adjacent constellation points differ by only 1 bit. So if you have coded in such a manner, then you can find out, compute the bit error probability, which would be the symbol error probability divided by log base 2 of m. So that was what we discussed in the last few videos, and today we would start discussing the error probability equations of different linear modulation schemes. So linear modulation schemes. So linear modulation schemes would include pulse amplitude modulation, it's also called PAM, phase shift keying, and quadrature amplitude modulation. So all the modulation where you can represent your transmitted signal as a scaled version of your model, those modulations are called linear modulation. And because the complex scale factor involved both the amplitude as well as the phase scaling, this allows this phase shift key and quadrature amplitude modulation also be called linear modulation. So remember your system model says that your Si of t, which is your symbol that you would transmit, would be nothing but real part of AI would be the amplitude. You can include a G of t, which is nothing but a pulse shaping filter that is typically used to improve the spectral efficiency of the transmission. We're not going in the detail of the pulse shaping here, but G of t is a pulse shape, but it is a normalized pulse shape. That is, its energy is still one, so it does not amplify the signal in any way. Times e to the power j 2 pi fct. That is your symbol to be transmitted. Now this AI is a complex number, and this would change for different types of modulation. For example, for pulse amplitude modulation, AI would only be real, and it would have values like plus minus 1, plus minus 3, like this. That means you would have for different values of I, your amplitude would increase. This means that for pulse amplitude modulation, you would have a linear or one-dimensional constellation diagram. You don't need a two-dimensional constellation diagram. You only need one basis function to represent all capital M symbols that you wish to transmit. In the case of pulse shape phase shift keying (PSK), your AI would be equals to some constant amplitude A times e to the power j theta I, where this theta I would normally can be represented as 2 pi by m times I minus 1. That means for different values of I, where I would take values from 1 to m, because there are capital M different symbols that you wish to transmit, and for different values of I you would have different values of theta I, and that would mean that you are talking about different constellation points on a circle with a constant amplitude. So the constellation points for the phase shift keying would lie on a circle of a constant length. This means your symbol energy ESI would be constant, in this case A squared, whereas the symbol energy ESI, which is by the way integral from 0 to Ts Si square of t dt, it would still be equals to AI squared, but your AI would be different in the case of pulse amplitude modulation for different values of I, whereas for phase shift keying, your AI would be constant for all constellation points. So hence it would be a constant envelope kind of a signal phase shift keying. And then in the case of quadrature amplitude modulation, you would have this AI would be equals to a complex number. So it would have some amplitude which would vary with different I, and you would have phase which would vary with different I. So quadrature amplitude modulation allows both amplitude as well as the phase to change for different constellation points. So now let's start with the pulse amplitude modulation. So let's look at the pulse amplitude modulation in a little more detail. So in the case of pulse amplitude modulation, we know that we would have a constellation point which is lying on a one dimension. So we need only um, one basis function per se in order to represent different values of the pulse amplitude modulation constellation points. That means say this is your phi 1 of t, and that's what you need. So you would have constellation points like this, and these would have different amplitudes, of course. So so let's suppose that from the origin this distance is d. This means you can have a distance of d here. So distance between these 2 points, this would be 2d. And then distance between these 2 points would also be 2d. So this point would come at, so if this is minus d, this would be minus 3d. This would be d, and this would be plus 3d. So this would, for example, in this case, we imagined m is equals to 4. And for m is equals to 4, you would have this one-dimensional constellation diagram. Thus, generally speaking, if you want to represent your amplitude AI in terms uh, of different I, for different I, that would be 2i minus 1 minus d minus m times d, where I would take the values of 1 all the way to m. For different values of I, you would have different amplitude. For example, if I is equals to 1, then this would mean that you're talking about uh, minus m plus 1d. That means in this case it is minus 3d. For I equals to 2, so this would be 3, and this would be 3 minus m. In this case, it would be minus d. And similarly, you would have for I equals to 2, you would have I equals to 3, you would have 6 uh, minus 1, that would be 5, 5 minus md, that would be equals to plus d here. And similarly for I equals to m, you would have values of plus, so values of, if I is equals to m, that would be means 2m minus 1, that would be equals to 3d in this case. So this formula of AI covers all points in the constellation diagram which you may have. And now if you want to compute what is the symbol energy ESI, so as mentioned earlier, so it would be integral 0 to Ts Si square of t dt, right? And we know that anything but AI would have a unit energy. So your energy depends on AI, and your energy would be AI squared. But your energy would be different for different values of I. So it makes sense to compute what is called the average symbol energy. So average symbol energy, let me call it ES bar, would be equals to 1 over m summation I equals 1 to capital M, um, the individual energies, which is AI squared. That would mean that would be equals to 1 over m summation I equals 1 to capital M times 2i minus 1 minus m squared times d squared. So that would be your average symbol energy. If you simplify it further, that would be equals to m squared minus 1 over 3 d squared. This is your average symbol energy, and we'll make use of that when we compute the error probability. So now if you want to compute the error probability, you can make use of what is called the nearest neighbor approximation. And remember, nearest neighbor approximation said that your symbol error probability is approximately equals to the number of nearest neighbors times q function of d min over root 2 n naught. So this is a peculiar kind of a situation where all but two constellation points would have two nearest neighbors, but the last constellation point, for example, in this case, this one or this one, only have one nearest neighbors. All other points except for these two constellation points would have two nearest neighbors. So you can write down the equation for the symbol error probabilities in an exact manner, and that would be equals to your symbol error probability PS would be equals to for m minus 2. So remember you would be talking about, you would compute the symbol error probability for each of the constellation points, and then you would divide by m to compute what is the average symbol error probability. So you have to divide by m to compute the average symbol error probability. And now for n minus 2 constellation points, you have two nearest neighbors, and then you would multiply this with q function of d min, which is nothing but 2d over root 2 n naught times, sorry, plus for two constellation points out of n, you would have only one nearest neighbor, and then you would multiply it with q function of d min, which is 2d over root 2 n naught. And now this q of 2d over root 2 n naught can also be written as q function of root 2d squared over n naught. If you take it common, then you would have n minus 2 times 2 uh, plus 2. So this would be equals to 2 into m minus 1 over n times q function of 2d squared over n naught. So this is a simple error probability. We have just simplified this equation down to this equation. So you can see that 2 times q function of root 2d over 2 n naught has been taken common, and then and the rest you would have m minus 1, m minus 2 plus 1, that would give you m minus 1 over m. So this gives you the total symbol error probability. But now you don't want your symbol error probability in terms of this d, which is arbitrarily defined, which should be connected to your symbol energy. But how would you convert this 2d square over n naught thing into something which is related to the symbol energy? So remember, we computed what is the average symbol energy. So this is related to d square. Right? What we want here is 2d square over n naught. So you can compute 2d square n naught over n naught in terms of your symbol energy from this particular equation. So will make use of this equation. And from this equation, this would imply that your 2d square over n naught would be equals to 6 times es bar over m square minus 1. And hence your average symbol energy, symbol error probability would be equals to 2m minus 1 over m q function of. So if you there would be an n naught here as well. So if you call es over n naught to be your gamma s, so it would be 6 times your gamma s bar over m square minus 1, where gamma s bar is nothing but es bar over n naught. In a way, this is related to signal to noise ratio for a particular bandwidth symbol interval product. This may be exactly equals to the signal to noise ratio, um, and we'll talk about that today as well. So this is your symbol error probability for a pulse amplitude modulation, Emery pulse amplitude modulation signal. That is called Emery PAM signal. And of course, if your signal are gray coded, you can then compute the bit error probability, and that bit error probability would be simply your symbol error probability over log base 2 of m. This would give you the bit error probability. So now once we have computed this symbol error probability of pulse amplitude modulation, as we have said, we have not gone into too much details. We have make use of the nearest neighbor approximation, and then we extended that concept to the constellation of pulse amplitude modulation. So we would continue with to look at the different symbol error probabilities of the linear modulation scheme. So the next would be your phase shift keying. So let's very quickly look at what would be the symbol error probability for phase shift keying. PSK. So we said that for PSK our SI of t, which by the way is written as real part of AI, G of t is your pulse shape, e to the power j 2 pi f c t. And this AI has a constant amplitude A, but it has different values of theta I, which is given by 2 pi by m, I minus 1, where I varies from 1 to m. In other words, you have divided the total phase of 2 pi into m equal parts, and you would have those as the constellation points. So, for example, if you have this circle of radius a, then you would have a constellation point here, you would have a constellation point here, constellation point here, you would have a constellation point here. For example, if m is equals to 4, this length would be a, so this is your amplitude, and remember this would also be equals to root of es, because your symbol energy esi would be equals to a square for all the constellation points in this case. So this root es would be your symbol energy under root, that is the radius of the circle as well. So now if you want to compute the minimum distance, so remember, so you can connect these two here like this and draw a perpendicular, and this would be, for example, 90 degrees, your right angle, and this angle, so remember this total angle is 2 pi by m, so this angle would be pi by m. So you can make use of a simple trigonometric identity, which can say that the sine of this angle pi by m would be nothing but this. If this distance you call d min, so this half of the distance would be d min by 2 times a. So this would be the identity that you can use, and this would imply that d min you can compute from here would be nothing but 2a times sine of pi by m, where a is nothing but root es as well. So you can say that d min squared would be equals to uh, sorry, if we talk about d min, it would be 2 times root es times sine of pi by m. And now, if you want to write out what would be your symbol error probability, then you can make use of the nearest neighbor uh, approximation, and your probability of symbol error PE or PS you can write would be equals to the number of nearest neighbors would be 2 times Q function of 2a times sine of pi by m over root 2 n naught. And then if you define Es over n naught to be your gamma S, then your symbol error probability can be written as 2 times Q function of root 4 Es over n naught times sine of pi by m. In other words, you have a symbol error probability that is equals to 2 times Q function of root 2 gamma S times sine of pi by m. So this can be an approximate symbol error probability equation for phase shift keying. So we would stop here, and in the next video we would see what would be the symbol error probability for a quadrature amplitude modulation, and we would restrict ourselves to square constellations.